Hi everybody, welcome back. In the last video we discussed Gauss's law, we discussed electric flux and how the concept of electric flux can be used to at least motivate the Gauss's law expression, which is that the flux coming out of a surface is always going to be equal to the enclosed charge over epsilon naught, which is a very useful result. And then we extended that and said, okay, you can figure out that the flux through any surface that surrounds a particular charge, well, make it a spherical surface just to make things easy, is going to be equal to, well, the charge divided by epsilon naught, regardless of the radius of our sphere. And we realized that if you have a bunch of charge sprinkled around, you could imagine making a bunch of little spheres around each of those Q1, Q2, Q3s, etc., and then filling in the space in between with other figures of whatever shape you want. And since there isn't any charge in those, then any flux in is also going to be flux out, so the net flux through those surfaces will be zero, and the only surfaces that will have non-zero flux will be the ones that enclose charge, which, just for the sake of our argument, we made little spheres, though, as we know, that was not necessary. And the overall result is that the overall net flux is equal to the enclosed charge over epsilon naught. But we also know that the overall flux is equal to the surface integral of E vector dot dA vector. And it's that relationship, the fact that the surface integral of E vector dot dA vector is equal to the enclosed charge divided by epsilon naught, which is going to prove extremely useful for us later in future discussions in this unit. So let's make a quick example of how to use Gauss's law to calculate the enclosed charge in a surface. Now, most of the time when you use Gauss's law in this course, it's going to be the opposite. You will have some way of figuring out via, often using calculus or via just geometry, what the enclosed charge is inside of a surface, and you're going to use that to come up with an expression for the electric field at any arbitrary position. In this situation, I'm giving you the electric field, and you're going to use that to figure out the enclosed charge. So here we have an electric field that has a certain direction, and it's always pointed in the same y and z directions. The y and z components of the electric field are constant at E sub y is 6 newtons per coulomb and E sub z is 7 newtons per coulomb. But the x component of the electric field varies with position in x. So what that means is that if we're going to figure out a net charge, then we're going to need to take into account that depending on our x position, we're going to have different values for the electric field. In other words, this is an example where we're going to need to use some calculus to calculate this flux. And then we'll use Gauss's law to solve for the unknown charge after we have used the calculus. So here we say, okay, start off with your given and your basic equation. The flux is equal to closed integral of E vector dot dA vector, and that's equal to the enclosed charge over epsilon naught. Okay, well, let's figure out that flux. The electric field, after all, is given to us from the problem as 3x plus 4 I plus 6j plus 7k in units of newtons per coulomb. And technically that should be 3x per meter plus 4I, etc. But you get the picture, so that the position units cancel when we plug in our x. But in any case, we have this cube that has an edge length of 2 meters, so each of these edges goes 2 meters from the origin in the y direction and the z direction, and goes to a position of x equals negative 2 meters in the x direction. So the idea here is that our closed integral over the surface is going to be equal to, well, let's just break it down. How about we say, okay, this is going to be a dot product, and each of these areas is either in the positive x or y direction, or positive x or z direction, or the positive or negative y and z directions, that is. So positive or negative x, positive or negative y, positive or negative z. So in any case, let's see now. Well, the there is no variable dependence on our y terms and on our z terms. So what that means is that since our y components and our z components are just constant, any flux in the y and z directions on one end of the cube is going to be canceled by flux out of the opposite end of the cube. So for example, at the lower surface at y equals 0, or sorry, at z equals 0, yeah, there is flux through the cube, but it has no y and z dependence. So at that particular x value, whatever flux comes in at that particular x value at the bottom of the cube is going to be equal to exactly that same flux out at the top of the cube. So any contributions from the y and z directions are going to be 0, because the bottom is going to cancel the top, or the left is going to cancel the right. What will not cancel is the back end and the front end, because there is x dependence on our electric field. So we're going to have to take that into account when we do our integration. So I got rid of the y and z terms because I know that they cancel. And they're not, each one is not 0. Beware. E sub y at y equals 0 is not equal to, it's not 0, and e sub y at y equals 2 is also not necessarily 0 either. But the point is that since the x's at a particular x, the y and z components are the same at that particular x, no matter what our y value is, or what our z value is for that matter, those parts are going to cancel. So the only thing that doesn't cancel is the flux due to in the x direction, those being the front and back parts of the cube at x equals -2 and x equals 0. Okay, so how is this going to work? Well, again, here we have our electric field vector. There's the equation for our flux, and then we have the result of our flux keeping only the non-zero terms, or at least only the terms that didn't cancel. So that's the x component of our electric field times the area at that point minus the x component of the electric field at that different point times the area at that point. And it's minus because one of them points out, the other one points in. In fact, what we're going to do is we're going to say that the back of this is going to be what we're going to call x2, and the front of this is going to be what we're going to call x1. So the areas are easy. Each of the areas is 4 meters squared, because the sides are of length 2 meters. So at the back end we have x2 equals -2 meters. At the front end we have x1 equals 0. Now, why did we have a minus sign right here? I thought this dot product stuff was supposed to be a plus. Well, and I thought this whole integral was saying that we were adding stuff together. So here's the thing. Yes, the integral is saying that we are adding things together, but remember what's inside of the integral, e vector dot dA vector. At the front end, the area vector is equal to 4 meters squared times I being the unit vector in the positive x direction. At the back end, the area vector is 4 meters squared times -I, because the back surface, the unit normal vector from the back surface points in the negative x direction. That's where we got this minus sign right here. Okay, so now it's time to finish this off. Well, plug in x1. x1 is 0, so the x component of the electric field at x equals 0 is 4 newtons per coulomb. But at the back end, at x equals -2 meters, the x component of the electric field is -6 plus 4, which is -2 newtons per coulomb. So there's where we're at so far. We already have our areas. Now it's just time to plug everything in. And when you plug everything in, it turns out that you end up getting each side has a positive flux, because the front end is positive because the electric field there is positive and the area vector there is in the positive direction. At the back end, the electric field is in the negative direction, and the unit normal is also in the negative direction. So that's a positive flux as well. In other words, we're dealing with this cube containing a positive amount of charge, because there's positive flux coming out of each end for that matter. So not only does the positive more than cancel any negatives, there are no negatives. So we have calculated the net flux now. But the problem was we needed to calculate the enclosed charge. Well, Gauss's law tells us that the net flux through our surface is equal to the enclosed charge divided by epsilon naught. So to get the enclosed charge, we just take the flux and multiply it by epsilon naught. So there's the flux. So the charge is epsilon naught times the flux. Plug in epsilon naught, plug in the flux, and you get an enclosed charge of about 210 picocoulombs, using two significant figures on this. So that is how we can use Gauss's law to figure out the value of the enclosed charge inside of our surface.